The goal is to get a better understanding of knee kinematics in order to improve implant design and alignment to achieve better patient outcomes after total knee arthroplasty. The workflow was initially created to align the axis of the specimen, as for example the flexion axis, exactly to the axis of the joint motion simulator with a closed capsule where it's not possible to directly assess the relevant landmarks. Today, we show modification of the initial workflow and align the specimen not according to its natural flexion axis, but the flexion axis of the implanted implant to accurately measure the kinematics of the implant within the specimen. First, we prepare the specimen to expose clean bone at the proximal femur and the distal tibia. Then we clean the tibia with acetone and attach measuring points. After attaching enough measuring points, we use the Aramis measuring system to acquire a 3D point cloud by rotating the bone stepwise. Then we use a previously created segmented CT scan of the tibia and fit it to the 3D point cloud. To check the accuracy of the 3D fitting, we first perform a visual inspection, followed by a quantitative inspection. Therefore, we use a touch probe. The tip of the touch probe has a known position relative to the touch probe points. When palpating the bone using the touch probe tip, the Aramis measuring system calculates the distance of the tip to the fitted CT scan. When the fitting is perfect, the distance of the tip to the fitted CT scan should be 0. Due to small segmentation errors, the quality of the CT scan, and the possibility of scraping off some bone during preparation, our accepted tolerance is 1 mm. However, the maximum deviation is usually much smaller. If the fitting is then good enough, we save the 3D fitting information, which contains the tibia points to CT scan information. Since the specimen was already prepared for implantation by an experienced knee surgeon, we can directly insert the tibial component, what also underwent a 3D fitting, and measure its position relative to the tibia with the Aramis measuring system. As we then know the offset between the tibial coordinate system and the implant coordinate system, we add the position of the implant coordinate system to the previous 3D fitting of the tibia. This is important since we want to align the specimen to the joint motion simulator based on its implant positions. Then we perform the same process for the femur. We attach the measuring points, acquire a 3D point cloud, and perform a 3D fitting. We also check the accuracy and then save the 3D fitting information. We insert the femoral component, measure its position relative to the femur, and add the position of the implant coordinate system to the previous 3D fitting of the femur. Afterwards, we use the CAD software to virtually implant the femoral component in the femur according to its measured position. Then we align the femur based on the coordinate system of the femoral component to the joint motion simulator and check how exactly the femur pod should be placed in the joint motion simulator that the femur can be embedded in the femur pod. If we found a good position, we assign the coordinate system of the joint motion simulator to the femur pod. Then we check the quality of the measuring points on the femur. If the specific point configuration is still detectable, we cut the femur and close the intramedullary canal with Play-Doh to secure the embedding process. In the same time, we perform a 3D fitting of the femur pod and the CAD file of the femur pod containing the coordinate system of the joint motion simulator. Afterwards, we place the femur together with the femur pod in the embedding fixture and acquire a point cloud of both. Then we insert the previously created 3D fitting files of femur and the femur pod, and due to the specific point configuration, the measuring system is able to match the files to the new point cloud. With this, we measure the distance between the femoral implant coordinate system and the femur pod coordinate system, which corresponds to the coordinate system of the joint motion simulator, and try to align them. After alignment, we embed the femur in the femur pod and acquire the exact position after hardening of the embedding material. Then we check the quality of the measuring points on the tibia, cut the tibia, and close the intramedullary canal with Play-Doh. Afterwards, we place the femur pod in the joint motion simulator in exactly the position we previously chose virtually. To ensure correct tibial alignment, we apply 50 Newton compression force and align the tibia to have 0° flexion by tracking again the measuring points of the tibia and the tibia pod. All other degrees of freedom result in a neutral alignment. After alignment, we embed the tibia in the tibia pod and acquire the exact position after hardening of the embedding material. In order to measure the kinematics of the implant within the specimen, we need to know the position of the tibial component coordinate system in relation to the femoral component coordinate system. Therefore, we again acquire a 2D point cloud of the femur and the tibia and measure the position of the tibial component coordinate system relative to the femoral component coordinate system and transfer this information to the joint motion simulator to accurately measure the kinematics and kinetics. After that, we start testing and perform a continuous knee flexion from 0 to 90 degrees by applying 200 Newton actual compression force with all other forces and moments maintained at 0. Due to the 3D fitting, it's possible to measure the resulting kinematics and also visualize them in the Aramis measuring system. That's how we try to improve patient satisfaction.